Let's consider that we just have a chunk of semiconductor material. Carrying some current I. If the charge density along the direction of the current is QD coulombs per meter, and the velocity of charge movement is V meters per second, then we can say that the current flowing through this is the charge density QD multiplied by our velocity V. So that we have coulombs per meter multiplied by meters per second gives us coulombs per second, which is obviously electrical current. Okay. Now let's consider an NMOS transistor. And I'm going to attempt to draw a 3D-ish representation of what's going on here. Pardon me. So this will be the surface of our substrate. And then let's put our gate here. And say that this region here is our drain. This region here is our source. And over here is our body connection. Let's short our body. Let's short our source. And let's short our drain for now. And here in the middle, we have our gate connection. And let's say that the voltage VG applied at our gate is exactly equal to our threshold voltage, which would mean that inversion has occurred. And so we have a channel here full of electrons, and the thickness of our channel, or the depth into the substrate, is effectively constant. Okay. So what I'm saying is there shouldn't be a slanted profile or anything here in this region. It should be a constant value. And I'm going to try to depict that with a little gray line here. Okay. So our charge distribution is constant. So the area underneath the gate of our semiconductor looks like this chunk of semiconductor material. Okay. Except that right now, we're not passing any particular current through it because we don't have anything that's pushing current. Okay. So at the onset of inversion, where VG is exactly equal to VTH, the charge density produced by the gate oxide capacitance has to be proportional to the gate voltage and the threshold voltage. For any VGS greater than VTH, any charge we put on the gate has to be mirrored by more charge accumulating in the channel. And so we're going to get a charge density QD is equal to W C ox VGS minus VTH, where W is the width of the channel. Right? So to be clear here, this dimension is the length of the channel. W is the width of the channel, and it has some particular thickness whose value actually isn't particularly important, so that we're just representing a rectangular box or rectangular chunk of semiconductor that has a lot of electrons, which could be asked to do something if we needed it to, right? So we have an evenly distributed charge density in this area given by W C ox VGS minus VTH. If we were to increase the voltage present at the drain, what will happen? So if let's say VD is a little greater than 0, and let's also say that VGS, so we're going to use our source as a reference here because it's at ground, is greater than VTH. What do we think should happen to our charge distribution? So this region here now has a positive electric potential. And there are a bunch of electrons right here. What are they going to want to do? They're going to want to move over. So we should see that we wind up having more electrons over here and less electrons over here because they're being attracted. And so what we'll have is a position-dependent distribution. So this guy right here is for VDS is equal to 0 volts. For VDS greater than 0 volts, what we get is something like this. QD is equal to WC ox VGS minus V of X minus VTH. V of X is nothing more than the potential of the channel, and it has to be position dependent because we have some electric field that's extending across the channel. So let's call this location 0. X is just some generic location in our channel where we will have some potential. And this endpoint here is L, the length of our channel. Well, since we have a positive voltage applied on this end of the channel, no voltage applied over here, we now have an electric field. Right? There's a potential difference across the semiconductor material that makes up our channel. We have an electric field. It should stand to reason then that we should see some sort of drift current, right? Where our drift current is going to be given by our charge density times the velocity. So we can say ID, where ID is a current that's flowing. Let's see. So the field is directed this way. So the current is directed this way. ID is a current flowing through the device from the drain to the source is equal to negative W Cox VGS minus V of X minus VTH times V. The negative sign comes from the fact that the electrons are moving in the opposite direction of the field, right? For a semiconductor, yeah, so yeah, this is per unit area, so I'm just kind of using them interchangeably, but absolutely. So yeah, let me go back through here just for the sake of argument and put primes. So typically speaking, what I mean between Cox and Cox prime is Cox is the capacitance and Cox prime is the capacitance per unit area. But for us, it's going to be effectively the exact same thing. It's just a question of units. It represents really the same quantity, but thank you. So we know that for a semiconductor, the velocity V is equal to mu, our mobility, times E, our applied electric field, and from physics 202, potentially ELEN 313, depending on how far behind Sandra is, which it sounds like she's reasonably far behind. Electric field is nothing more than negative the gradient of the voltage. You got there. Great. Wonderful.
Just turned in that homework.
All right. So if we put these two relationships in, substitute these two relationships into our drain current equation, we find that ID is equal to positive W Cox VGS minus V of X minus VTH times mu n, since we're dealing with electrons, multiplied by the derivative of the positional potential with respect to position. So what I'm going to do now is I'm going to multiply both sides by this differential line element dx, and then integrate both sides, right? So I'm going to integrate from 0 to L ID dx. And on this side, I'm going to integrate from the potential at x is equal to 0, which is 0 volts, because that's our source, right? And our source is still tied to ground. And at X is equal to L for our drain, our potential is VDS. Mu N W Cox prime VGS minus VX minus VTH EV. And if I do that integration, the result will be the following equation. ID is equal to mu n Cox W over L VGS minus VTH multiplied by VDS minus 1/2 VDS squared. And this is valid for VDS is less than or equal to the quantity VGS minus VTH. So this is one of the multiple current voltage relationships that we're going to have for a MOSFET transistor. Okay. This region, VDS less than or equal to VGS minus VTH, we are going to call the triode region. We have, or we can see that our current here depends on two voltages. The last term, VDS, V, yeah. So this is VGS for goofy, VDS for daffy, VDS also daffy. I guess I should have said Donald, so it would have all been Disney characters. So GS, this VTH, actually this is supposed to be the threshold voltage, so that's supposed to be lowercase h, isn't it? Because I have so many different VTHs, so I guess I need to fix that. So that's definitely not the Thevenin voltage because we don't have anything Thevenin here. Let me go back and fix these. I apologize, I'm going to get confused. Yeah, I know. I mean, we have Thevenin, thermal, threshold. I think that's it. I say that, and then I'm going to be like, oh yeah, it's the thyristor voltage or something. That's also going to lowercase h, lowercase h. Okay. I want to also give you a new name for this quantity, VGS minus the threshold voltage. We're going to call that the overdrive voltage. VOD, or overdrive voltage. And this simply represents how far past inversion we've gone, right? So we've gone beyond a point of turning the transistor on, and we've applied some amount of excess voltage. Okay, so that's why we're calling it an overdrive voltage. So if we were to plot ID it would look something like this. So let's plot our drain current on the y-axis. Our drain source voltage on the x-axis. And I'll do these in different colors. I'm trying to do this. Actually, that one should go a little bit further. Let's see. I'll do gray. This dashed gray line that I'm attempting to draw here should look roughly parabolic. Okay. Each of these different curves correspond to a different overdrive voltage. So let's call this first one VGS1 minus VTH. Call the second one VGS2 minus VTH. The third one will be VGS3 minus VTH. And VGS4 minus VTH here, okay? Now, because of this square dependency on VDS, we should expect them to actually fall down after they reach the top or the peak of their arc. But since this equation is only valid for when the overdrive voltage is below this, that's why we're going to stop our graphs right here. So this region of our graph to the left of this parabola is our triode. Okay. And I'm going to call this area that I'm about to circle in purple the deep triode region. Okay. So this area is important because we have a nearly linear current voltage relationship, which means in this particular region, at a large signal analysis, our transistors are behaving like a resistor. So we'll define the limits for this as VDS is much less than twice VGS minus VTH. And in this region, our drain current relationship simplifies to mu n Cox W over L VGS minus VTH. Sorry, that should be lowercase h. Multiplied by VDS. So effectively, if VDS is much smaller than our overdrive voltage, we can throw away the square bit, because when we square something small, it's even smaller. Right? And we have a linear relationship between ID and VDS, which we can call, I'll sneak it in here, R on is mu n C ox W over L VGS minus VTH. This whole thing is a -1 power. So for very specific bias voltages, we can make this guy behave like a resistor, which is fantastic in integrated circuit design, because the physical size of a transistor is usually much, much smaller than the physical size needed to implement a resistor. All right. So this is triode region operation. Any questions? Luke?
How big would that be?
So it depends on the size of the overdrive voltage, right? So without getting into a wild amount of detail that is going to mean less than nothing to most of you, because you're not going to want to take my integrated circuits class in the fall. The resistance of a section of N-well material, so that's just effectively doped N-type material, typically on the order of several hundred ohms per square. So when we're dealing with resistors and resistances in integrated circuits, we're typically dealing with what's called a sheet resistance. So what that means is that if I have a square, it does not literally matter what its physical dimensions are, but if it is a square of material, it has a particular resistance. So if I have one square that is 800 ohms, two squares becomes 1600 ohms, etc. But if I were to do something dumb like this, that's actually just one square. It's just bigger, so it's still 800 ohms. So anyway, the sheet resistance of a section of N-well material is 800 ohms. The sheet resistance of high resistance polysilicon is usually on the order of somewhere around 1.1 to 1.2 kilo ohms per square, etc. So we have to make things physically large due to the design rules to get large resistances. The resistance of a MOSFET transistor is tunable depending on what our voltages and things like that are. So we can very often achieve comparable resistances to an N-well resistor or a high Z poly resistor with a small transistor utilizing much less space. To get really large resistor values is going to be hard here, because resistance is effectively going to be, voltage over current, right? So to get a high resistance value, like very large resistance value, we need a very low slope. And this is the beginning part of, like, this is the linear part of an upside down parabola, if that makes sense. So this parabolic relationship is curving down like this. So we're seeing a large change in current due to a relatively small change in voltage. So we can't achieve really, really large resistors, but we can get small resistors in a smaller package than we can by just making really long runs of material. Does that make sense, Logan?
So you said you can tune a MOSFET. Can you tune a fish?
You are a jackass. Any relevant questions? All right, let's move along then. Oh my gosh. So I'm going to draw another picture here. Not going to do it 3D style this time, but it's effectively representing the exact same thing as we talked about before. Here in the middle, I'm going to have my gate. Actually, I should draw this a little larger. So it'll be easier to see what's happening. So that's my gate. Here's my source. Here's my drain. Here's my body. Let's continue to keep our body terminal grounded. Let's continue to keep our source terminal grounded. Let's make our gate source voltage VGS greater than our threshold voltage so that we have a channel. And now let's make our drain source voltage greater than VGS minus VTH. Our drain source voltage is greater than our overdrive voltage, okay? So when VDS is exactly equal to VGS minus VTH, the profile of our charge distribution looks like this. So it stays the same here, and then it, what we call, pinches off here, okay? Our channel inches off. Let's define this distance. This is 0. This is L over here. Okay. So we're going to redo our integral. Well, actually, let's talk about something else just real quick, okay? So when VDS is exactly equal to VGS minus VTH, we have this profile where it's pinched off. When VDS is greater than VGS minus VTH, this pinch off location moves closer to X is equal to 0. So it moves into the device like so. So let's call this distance here L prime, which would be an arbitrary distance where we are a little bit beyond pinch off. Our integral from 0 to L prime, we're going to have ID dx is equal to 0 to VGS minus VTH, UN, C ox, W, VGS minus VX minus VTH. I keep drawing capital H's, I apologize. dV. And performing this integration gives us ID is equal to 1/2 mu n Cox W over L prime, which is going to be pretty much L VGS minus VTH squared. Well, this is true for, sorry, my thing moved on me, VDS is greater than or equal to VGS minus VTH, okay? So our drain source voltage is larger than our overdrive voltage. Our charge density profile becomes pinched off, and we see that our current is no longer dependent on the quantity VDS. It's constant for VDS. Okay? So this is what we call the saturation region. Because an increase in our input voltage, VGS, does not generate, an increase in our input voltage, VDS, does not generate a corresponding change in our output current. So if we look at our graph up here, what we should observe is that it just effectively flattens out, stays constant. Like so, where everything over here to the right is our saturation region. So effectively, we have a constant current. Now, that constant current, I'll go back to that in a second, is only true when this quantity L prime is very close to the actual channel length. Okay. So what we're going to talk about next is the concept of channel length modulation, which is effectively the early effect for MOSFET transistors, okay? Because as our voltage VDS increases, we push that pinch off point further and further and further to the left, shortening the length of the channel, thereby increasing our drain current, okay? Very, very similar to how the early effect worked. The early effect, further reverse biasing our base collector junction caused the width of the base to decrease, which caused our saturation current to increase, which in turn caused our collector current to increase. Here, we're shortening the length of our channel, which is causing ID to go up. So it's effectively the exact same thing. Before we talk about that in terms of any math though, this curve looks effectively the exact same as a BJT, except the names of the regions are significantly different, which is absolutely something that can be confusing, right? So for a MOSFET transistor, when our current is stable and constant, we're in the saturation region. In a BJT transistor, we call this what? What's the region of operation where the collector current doesn't depend on or is independent of, gosh, which voltage is it? VCB. Forward active, right. So saturation region is analogous to the forward active region. And then this region here, our triode region, where our current is a function of VDS, is analogous to the region in BJT operation, where our current is actually dependent on our base collector voltage or our collector emitter, same effective thing. So triode is the same as saturation in BJT. So we have two different saturation region operations, which mean vastly different things for the two different devices. So I would encourage you guys to try to wrap your head around these things and get an understanding of what saturation means for MOSFETs and what saturation means for BJT, so that you don't get the two of them confused, because that's obviously going to be a bit of an issue when we're working with these things. Okay. Cutoff region is effectively the same thing, means the device is off, so there's no difference there. Good for us. And then, like I mentioned a moment ago, and what we're about to talk about, the concept of channel length modulation is effectively the same thing as, or at least it looks the same as the early effect did for BJT. So, channel length modulation. Effectively, since the position of the pinch-off point depends on VDS, the device current is not actually constant in saturation operation. So for a single value of overdrive voltage, this is ID, and this is VDS. The expectation, this point right here, represents VDS is equal to VGS minus VTH, right? So this is how we expect it to behave, because the saturation equation tells us that we should not see any increase in current, okay? But because our channel length is actually getting smaller, the higher VDS is, we actually observe simple linear increase in ID. Where this ID is given as 1/2 mu n C ox W over L VGS minus VTH squared times 1 plus lambda VDS, where lambda is what's called a channel length modulation, which I'm going to abbreviate as CLM coefficient. And what it represents is the relative change in channel length for any given VDS. So what this means is that if we have what's called a long channel device, we're going to have a small value of lambda because it's going to take a really large value of VDS to cause that pinch off point to move by any considerable amount. Whereas if we have a very short channel device, like most modern MOSFET transistors that are used in electronics like modern computers and all that kind of stuff, lambda is going to be very large because if we have a channel length that's only a couple of nanometers, causing that pinch off point to vary by a nanometer isn't really that hard. Whereas if we have a channel length that's a couple of hundred microns, moving that pinch off point by 1 nanometer effectively doesn't change the channel length at all, okay? So we should see that this is very small for large L and very large for small values. All right, I think that's all I'm going to talk about today. I have a page and a half of notes on sub-threshold current operation, but I've never actually seen that used in a single problem on any textbook or anything like that. So it's more of a kind of general information. And effectively, all sub-threshold current means is that even if you don't have strong inversion yet, there's still some charge carriers in the channel. So if you applied a potential difference between the drain and the source, a very small amount of current will flow. We could beat it to death with math if we wanted to, but there doesn't seem to be any point because there's never anything beyond that. So let's knock off 20 minutes early, and I'm going to go work on grading your exams. All right. Okay. So let's see. So we covered MOSFET IV characteristics in one day, and I think I had 2 days dedicated to it. So we'll spend some time doing DC biasing of MOSFET circuits on Monday, and then maybe we'll do PMOS transistors one day, and then we probably will have time to do a review and stuff before the next exam. Sound good? All right. See you guys next week.